So, hi everyone once again. My name is Filipp. I am a machine learning engineer at Nebius, responsible for the infrastructure. And in our team, we not only fine-tuning and aligning models, but also pre-train large neural models from scratch. Right now, actually, we are training a 300 billion parameters mixture of experts model on more than 1,000 of on more than 1,000 of the GPUs. And as you all might know, that hardware is a very unreliable thing. And I want to share with you the lessons we've learned along the way how to quickly detect and disable malfunctioning nodes, along with how to quickly restart in case of failure. And one more thing I would like to share with you is, as you might have noticed, I am stuttering a little bit, so my pace of speech might be weird sometimes, but I hope this wouldn't diminish the value of information I would like to share with you today. So, to start with, when training LLMs in a multi-node, multi-GPU setup, we typically employ a data parallelism where we split input data across the batch axis, feed each part to independent model replicas, obtain gradients, average them with some all-reduce algorithm, and then use these gradients to update each model replica independently. But in case of failure of, as the training process is synchronous, in case of failure of any node, we can calculate gradients for this part of input data, so we can aggregate them. So in modern frameworks like JAX or PyTorch or TensorFlow, for example, what this usually means is that we have to recreate the entire training process from scratch. And given the long durations usually involved in training a very large models, encountering hardware failures is kind of inevitable, and this may stem from various reasons. For example, hardware failure, problems with CPU, RAM, network, data loading issues, as we usually stream our input data from external source, data center issues with power supply, for example, or some software failure. So in order to preserve the progress during training, we periodically save our entire training state to some persistent storage, and in case of failure, we quickly reload from it to continue our training from the last checkpoint. It's also to ensure a very good hardware utilization and automation. We want to quickly and automatically detect broken nodes and replace them and replace them with the good ones. One moment. To start with, how we approach at solving such problems, we are using Kubernetes for the cluster management, NVIDIA GPU and network operators for setting GPU nodes up, and the Argo workflow for initializing terrain workers and handling restarts in case of failure. So when training process starts, Argo creates a required amount of terrain workers, and in case of failure of any of them, all pods are getting destroyed and then recreated from scratch. We have implemented a multiple layers of hardware failure detection. We are using, for example, we have inbuilt Kubernetes node health check that automatically disables nodes that are unreachable for some reason. Maybe they're rebooted or something else. Also, we have implemented regular automatic checks that we will talk about a little bit later. And while NVIDIA GPU operator can automatically detect and disable some malfunctioning the GPUs, we have noticed that it sometimes overlooks some obvious issues like this, where NVIDIA SMI returns some error that clearly indicates that something with this node is wrong. So in order to overcome this problem, we have implemented a daemon set that periodically on each node checks exit code of the NVIDIA SMI and disables node that whose exit code is non-zero. Another very important and hard problem we have been faced with is as the training process is synchronous, on each training step, all workers have to wait for all to finish process their part of work. So if any worker is slower than the hours, then all workers have to wait for it. And in our case, what if one node is underperforming? Then for us, all nodes seem to underperform in this case. And we have found quite, I think, a good solution for this is that we conduct an hourly NCCL all reduce performance test on each node and disable nodes whose reported performance is lower than a given threshold. And we also found that this is a very good proxy metric for not only for detecting problems with GPUs, but also with RAM or CPU, as usually this also affects NCCL test performance a lot. One more thing we have been faced with is in some rare cases the training process just deadlocks, and to quickly detect and restart. In this case, we have implemented a health check mechanism that on each successful training step, we are updating an empty file in master worker file system, and along with Kubernetes inbuilt pod health check mechanism, we are checking that at any given point in time, it was updated recently. So if it is not, then the training process probably deadlocked, and we have to trigger a restart mechanism. One more thing about health check mechanism is that we have to carefully configure startup probes in order as the training process sometimes naturally pauses for things like checkpointing or validation. So in order to avoid false alarms, we have to configure it properly. So to quickly sum it up, we are using checkpoints to ensure a recovery in case of any failure. We use Kubernetes and some basic diagnostics mechanism to disable completely broken nodes, and we are using regular NCCL tests to disable slow performing nodes. One moment. Yeah, and as I mentioned earlier, we are using a checkpointing mechanism to preserve progress in case of any failure, and typically for the large language model, checkpoint size sums to 12 bytes per model parameter, as it consists the model parameter themselves in full precision and the optimizer state in full precision. And the optimizer state consists gradients running mean and running variance for all model parameters. And in our case, with a 300 billion per parameter model, this accounted to more than 3.5 terabyte training state. Yeah. And the naive writing approach would be just to write entire training state from single worker to persistent storage, but in our case, as the network with persistent storage is relatively slow, this would be a very, very long thing. So instead, we've come up with distributed write approach, where in our case, each worker writes a globally unique shard of model parameters whose full union is entire training state. So as you can see on this picture, if we have 4 workers, each of them writes a quarter of all tensors in the training state, and the persistent storage ends up with an entire copy of the tensor. And this approach allowed us to achieve a linear scaling of checkpointing writing time, and reduced it to just a couple of minutes. But that's still a couple of minutes of a very valuable GPU time. So because when we starting to checkpoint, we have to pause entire training process for a couple of minutes. So in order to further mitigate this interruption, we have implemented a two-stage approach to checkpointing. During the synchronous stage, we are copying entire training state from GPU to RAM, and this is usually very, very fast, as the interface between GPUs and RAM is measured in hundreds of gigabytes per second. And the second asynchronous stage, where concurrently we are copying training state from a RAM to persistent storage as the training process continues. Okay, we have handled writing and saving progress in case of failure, but there is still a lot to improve. We have noticed in our case during restarting after some failure. So in our case, we have noticed that two major time-consuming things were restoring state from persistent storage and compiling a JAX computational graph. For the latter issue, we have found quite a straightforward solution, as JAX offers a compilation cache as the experimental feature, which we are storing at the network disk. And this method allowed us to reduce the time required to compile model from 15 minutes to just a matter of tens of seconds. And for the first issue, we also come up with more strategic solution. And once again, in the naive case, we can just read entire training state from persistent storage to each model replica. But this, once again, in case of a very big training state, would be a very slow over standard network interface. So instead, we've come up also with a distributed read approach, where similarly each worker reads an entire globally unique shard of model parameters to its memory, and then broadcasts it with a super fast InfiniBand interconnect between nodes. And this is like, it doesn't matter the size, it's always just a couple of seconds. And this is also allowed us to achieve a linear scaling with the number of nodes and reduced reading training state time to just a couple of minutes. To quickly wrap it up, training big AI models on a lot of computers is kind of tough, but we've come up with some interesting ideas how to solve them. We use Kubernetes for organization. We keep an eye on the system health, and have gotten really good on saving and reloading our work very quickly. And Thank you very much for your time. I would be happy to answer the question that that you have, and further discuss potential problems and their solutions than training models in a large scale setup. Thank you once again.